All right, moving on with dilations, this time talking about angles. We're going to start with the same thing we started the last lesson with, is a review of the properties of dilations. We know two things about dilations: that a scale factor is applied, which will either enlarge or shrink the original figure, and we also know that any image will be parallel to its original pre-image. So those two things will continue to apply as we go through this lesson today. So we're looking at exercise 1, we're looking at the diagram that had angle BAC. So the dilation has already been done from point D, and point D is up here. And what ended up happening is all three of these points, A, B, and C, are now twice as far away as they originally were. So you can see this, if you'd like to check it, by drawing a ray that connects D through A to A prime, D through C to C prime, D through B to B prime, and then just lay your compass down and check that it's in fact twice the distance if you'd like to check it. But that's how the dilation was done here. List all parallel rays. Well, ray AC is parallel to ray AC prime, and ray AB is parallel to ray AB prime. So we have those two sets of parallel rays done here. If you take your protractor out, what you should see is that both angles 1 and angle 3 are 35 degrees. And that's just checking with a protractor. So to give a reason based on the property of dilations for why these two measures will always be the same, what we want to think about here is that because these two AC and A prime C prime rays are parallel, then angles 1 and 2 will have to be equal. That's the concept of corresponding angles. So establishing parallel rays through dilation creates equal angles. And then also these two parallel rays, AB and A prime B prime, when those are parallel, we have another set of corresponding angles 2 and 3. So if angle 1 is equal to angle 2, and angle 2 is then equal to angle 3, by substitution, we can say that angle 1 is equal to angle 3 without having to measure them. So generally speaking, if we have a dilation, angle measurements will be preserved. They're going to stay the same. All right, so that's the third property of dilations now, that they are angle preserving. So we'll never have different angles when we do a dilation. That's going to be extremely important as we get to trigonometry, which is coming. We do have segment lengths changing in dilations, but we do not have angle measurements changing in dilation. All right, exercise 2, if triangle DEF is dilated by a scale factor of 5, which of the following statements would be true? All right, so if I look at choice 1, it's saying the new angle D prime is 5 times the original angle. Well, we just said that angles are preserved, so that's definitely not it. We're not going to have a change of angle. Same thing here with number 3. The original angle E is 1/5 of the new angle. First of all, we would be applying the scale factor to the original, not the new. But we could think of it as a reciprocal, though. So, right, a scale factor of 5. This would potentially work if angles changed to divide the new one to show the original. But again, scale factors don't apply to angles. So both choices 1 and 3 are not correct. When we look at item 2, the original segment is 1/5 of the new segment. So like I just mentioned, we typically apply the scale factor to the original to get the new. But if I had a 5 attached to my DE to get my primes, that's how we would usually do it, I could solve for DE by dividing by 5. So this 1/5 on the new is equivalent to multiplying the old by 5. So choice 2 is correct because that segment length has been dilated. Choice 4, I can apply a scale factor with segments, but the thing is it's been applied in the wrong place. So that 5 should be multiplied by the original, not the new. And so this would not be the correct scale factor. So choice 2 is correct for that reason. All right, moving on. Exercise 3, we have E prime, F prime, G prime having been the result of a dilation of triangle EFG. We have an unknown scale factor. And so the first step is to take some tracing paper and verify. So if you just lay tracing paper down on triangle EFG, what you should be able to do is trace that triangle and then slide it so that angle F lands on F prime. That should be the same. Angle E lands on E prime. That should be the same. Angle G lands on G prime, and that should be the same. So you can just check those anecdotally with your tracing paper. To graphically determine the location of the center of dilation, we're going to mark point D and leave all construction marks. So the way we determine that center point is simply to connect our dilation points to our original points and trace the path backwards, essentially. So if I connect F prime to F and extend it back, and connect G prime to G and extend it back, wherever those two paths cross had to have been the dilation point, because they both have to travel out and connect through their pre-image to their images. I could do E and E prime too, but it only requires two to find an intersection point, so any two of those paths will be sufficient there. So that's how we find that, just with a straight edge. So using our ruler to measure lengths, we can calculate the scale factor. If I measure DF or DG, I can figure that out. I also can do it by measuring the segment lengths, right? So I can measure FG, and that's actually what's done down here. You can measure FG and measure F prime G prime to see how many millimeters those are. These scale factors are coming out pretty close to each other. There's a little bit of error in rounding here, but they're roughly 1.5 for each one. So that tells me the dilation was 1.5. If I wanted to check it from point D, though, I'd have to measure DF and DF prime. I wouldn't want to measure FF prime. That wouldn't give me any useful information. And then I could do the same thing with DG and DG prime. So the scale factor can either be figured out with the pre-image and the image, or with the paths that the points travel from the dilation center. All right, exercise 4, in diagram of triangle ABC, D and E have been located on AB and AC such that DE is parallel. So what it's telling us, it's not telling us how far along that segment they are. What it's telling us is that DE is parallel to BC. So give a dilation that will map BC onto DE. Let's think about that first off. If BC is going to be onto DE, what kind of scale factor would that need to be? So it's going to be a reduction in size. So the scale factor would have to be less than 1 in order for BC to map onto DE. So if I take the new image, DE, and divide by BC, that fraction represents a scale factor less than 1. So that's my dilation factor. No numbers are needed in this case, because whatever DE is, if I divide it by BC, I'm going to get a fraction less than 1, and that will indicate my scale factor. So what that does is it creates the new segment, and it will be a parallel. In part B, if triangle ABC was transformed using the dilation that we just talked about, would it be congruent? Or explain why the primes would be congruent. Well, if B dilates back to B prime and C dilates back to C prime, we're going to have the same 3 vertices. So the 2 triangles would have to be congruent. So what this is basically saying is, would triangle A, B prime, C prime be the same as ADE? And because the scale factor used DE to produce the dilation, they would have to be exactly the same points and therefore would be congruent. All right, so now putting numbers into this, and you can just use that diagram that you have there. If AD is 10 and AB is 15, you can indicate that like I have it here with that full segment marked. Then BC is 12 and AE is 14, so those are marked as well. We can algebraically determine the lengths of DE and AC because the AD and AB segments will give us our actual scale factor. So the original image was AB, the new one was AD. We're supposed to divide new by old. So 10 divides by 15 gives us 2/3. And that 2/3 can then be applied to the other figures, right? So to get from BC to DE, the scale factor has to be 2/3. So DE is going to be 2/3 of whatever BC was. So that's why we get 2/3 of 12 equals 8. What ends up happening with the second one, to get from AE out to AC, that actually goes the other way. So that's going to be a reciprocal relationship, which would be 3/2. But setting up it as a proportion, you could say that this AE segment is supposed to be 2/3 of AC. So that's what this fraction is showing. We know what AE is. It's 14. So we can say 14 over AC is equivalent to 2/3. So breaking that down just a little bit further, AE is the short segment, AC is the long one. So I want to set up that proportion the same way as 2/3 is. So 14 over AC equals 2 over 3. You can just do a cross product. You end up with AC equals 21.